Well, I would like to thank the organizers for the opportunity to speak at this wonderful conference. So I'll be talking about three-dimensional mirror symmetry, mostly the work that I did with Jacques Dissler at UT. But anyway, it's fine. Yeah. So the main players in this story will be n equals to 4 affine quiver gauge theories in 3 dimensions. So as we know, in type 2b, these guys have a description in terms of k d3 branes, with the d3 brane wrapping an R21 across a compact direction L with half BPS boundary conditions at the two ends. This is the famous Gayoro-Witten or Hanane-Witten picture. And then there is an equivalent type 2a description where you have k d2 branes with a transverse ALE space, and there could be d6 with O6, possibly with O6 planes wrapping the ALE. And this type 2a picture has an equivalent M theory description where we have km2 branes sitting at the singularity of a transverse ALE cross ALE space with possible G fluxes. Now we'll find this M theory description pretty useful in classifying mirror symmetry as we go on. But let's first ask ourselves why it is interesting to study these theories. Of course, there are many reasons. But one important feature of these theories is that they exhibit these exotic IR dualities, like mirror symmetry, for example. And also, the Higgs branch of such theories are instanton moduli spaces of G instantons on ALE spaces with instanton number k, the k being the number of D2 branes. Okay? So the rank of this group G is related to the number of D6 branes that you have. Okay? So I won't talk much about the second point. I'll mostly be talking about the mirror symmetry part of these theories. So since Peter already mentioned in good detail the field theory part of n equals to 2 and n equals to 4 supersymmetric gauge theories, I'll be quick with these slides. So it has n equals to 4 SUSY in 3 dimension has 8 real supercharges, which transform in a 2, 2, 2 of the SL2R and the R symmetry groups. Under R symmetry group, this is how the vector and the hypermultiplets transform. As you can see, it's asymmetric under SU2 and SU2R, SU2L and SU2R. So as a result, one can have twisted multiplets where the SU2R and SU2L are exchanged. Okay. In the IR, these theories flow to a superconformal fixed point. An IR limit is also the strong coupling limit of the gauge theory. There are 2 distinguished branches, as we know, Coulomb and Higgs branch, both hyperkähler manifolds. And the metric on the Coulomb branch is parametrized by the hypermasses, MIs, which are triplets under SU2L, while the metric on the Higgs branch are parametrized by these Fi parameters zeta I, which are triplets under SU2R. And they could both be understood as vector or twisted vector multiplets in the Lagrangian description of the theory. So what is mirror symmetry? It's a strictly IR duality between 2 theories with very different UV descriptions flowing to the same n equals to 4 SCFT. So what it does is that it exchanges the Coulomb and the Higgs branches and exchanges the SU2R with the SU2L. Now this naturally implies an exchange of background vector and twisted vector multiplets, and as a result it implies an exchange of hypermasses and Fi parameters. Now under this duality, masses on one side are mapped to Fi parameters on the other side, and the linear transformation that actually captures that map is called the mirror map. So once someone gives you a mirror duality, the mirror map is probably one of the most basic information that you want to know about the duality. Okay, so this is finding the mirror map will be one of the tasks that we perform in course of this talk. So how is mirror symmetry related to string dualities? So in the type 2b, mirror symmetry is simply S duality. So D3 is, of course, self-dual. NS5 goes to D5. If you have orbifold 5 plane, it goes to an O50, which is a coincident O5 minus with a D5, and so on and so forth. I mean, any half BPS boundary condition you give me, I can, in principle, write down the S dual of it. In the M theory, as I said, any supersymmetric gauge theory of the affine type could be understood as in terms of k M2 branes probing an ALE times ALE transverse space. So now, if we think of deforming one of the ALEs to an ALF, and we descend it to a type 2A picture, we have k D2 branes with some D6 branes wrapping in the other ALE. Okay, so that gives you a wall volume gauge theory on the D2 branes, right? Now one can do the same with the other ALE, and again that gives you a wall volume gauge theory on the D2 branes. Now, of course, these two theories in the IR are described by the same M theory background, which is just R2, 1 times ALE, and that is basically mirror symmetry. Okay, in the IR you have the same description for two different looking gauge theories. Now, so we'll find it useful to classify such mirror duals as this doublet gamma 1, gamma 2, where gamma 1 where gamma 1 is the singularity of the ALE1 and gamma 2 is the singularity of ALE2. Okay, so we will not consider exceptional singularities. We'll just stick to A and D type singularity for the obvious reason that there is no known way of deforming an E type ALE into an E type ALF. Okay, so now we are in a position to state the basic result. So we know that localization of SUSY gauge theories on S3 can actually provide a very interesting check for dualities in 3D, and mirror symmetry is an example. So what you do is that you compute objects like partition function on both sides of the duality, and you basically compare them. And since it's a case of two different UV theories flowing to the same IR theory, these two objects should agree. Now, Kapustin and collaborators in the 2010 paper basically worked out the details of this duality using S3 partition functions for theories that only consist of NS5 and D5 branes, okay, in addition to, of course, D3 branes. Now, one of the interesting things that they showed in course of doing that was that if you are given a SUSY gauge theory which consists only of NS5 and D5 branes, then the S3 partition function can be factorized into very neat contributions of NS5 and D5 building blocks. Okay, so I can write the partition function as a product of NS5 and D5s. Okay, and that's generic. No matter what the theory it is, as long as it is made up of NS5 and D5, and I know these building blocks, I can compute what is the S3 partition function of that theory. And an obvious result of writing the S3 partition function in this form is that the action of S duality at the level of partition function is obvious. So it's just a very trivial change of variables at the level of partition function. So it not only factorizes this in this very nice form, it makes the action of mirror symmetry or S duality very obvious in this construction. So what we do in these two papers is to basically extend the computation for the class of quivers which are labeled as an A-type ALE and a D-type ALE. So gamma 1 is Zn and gamma 2 is Dm. I'll explicitly write down what those quivers are, but these are, of course, very different from what Kapustin and collaborators worked with. Now, in the type 2b picture, this leads to understanding of new building blocks, namely orientifold 5 planes and orbifold 5 planes. And we explicitly derive these contributions at the level of the partition function level in the same way that Kapustin did for NS5 and D5. And as a bonus, we kind of can read off the mirror map just by looking at the two partition functions. Okay, probably I should just pause here and take questions if there are any. Okay, yeah, sorry. Say it again, what?
What distinguishes NS5 from D5 in the picture of the theory on Chern-Simons copy?
What is NS5? What do you mean?
What is the difference between those two theories once you put on S3? Is there some difference in Chern-Simons copy?
No, these are just Young-Mills theories with flavors. So what I mean is that if you write down the S3 partition function, you can identify pieces which are NS5 contributions and D5 contributions. Sorry, what? They're not conformal in the UV, yeah, but they flow to a SCFT in the IR, yes. Right. All right, so let's start with the classification. I'll go through this really quickly. So when one of the singularities is of A type and the other one is trivial, you have this kind of a quiver diagram where you have a UK gauge group with one adjoint and n fundamental hypers. On the other side, you have AN type of AN minus 1 type quiver with one fundamental hyper. Now this is very well known. This is one of the examples that Jan de Boer and collaborators studied back in the days. And the type 2b description of this thing is also very well known. It involves these D3 branes wrapped in a circle, and then with an NS5 brane and a bunch of D5 branes, and it's S-dual. Similarly, if both singularities are of A type, you get this kind of a quiver diagram, and this is also very well understood. Now, interesting things start happening when one of the objects, one of the singularities is of D type. So note that this is a affine D type of quiver with a bunch of fundamental hypers, and its mirror dual is a truncated AN quiver. So you have an AN quiver, you orientifold it, and this is what you get. So all the black dots all the black blobs are basically U2K. I don't know if you can see it. They're U2K gauge groups, and the terminal ones are SPK. Okay, so these are the dual theories. Of course, I mean, for this is a picture for generic N and M. For particular N and M, you will have more of such theories. I mean, there are more infinite families of such theories, but this is like what a generic mirror pair looks like. Now, the type 2b description of such theories have been well known, actually. And this is the work of Hanani Zaffaroni, and part of this was also covered in the second paper of Gayodobit in this duality paper. So in the B theory, what you have are these O5 planes, which are O5 minus planes with coincident D5 planes on both sides. And you have n over 2 NS5 branes and m minus 2 D5 branes. Okay, so the NS5 branes correspond to the U2K gauge groups that you see here, and the terminal SPKs come from D3 branes ending on O5 planes. Okay, so that's where the new thing comes in the boundary condition. D3 branes ending on O5 planes and their corresponding S-dual picture. Now, if you take n of Zn to be odd, you get another infinite family of mirror duals, and this time you see that this is on the A theory side. It's again a D-type quiver, but on the mirror dual, one of the SPKs have been replaced by a U2K and an antisymmetric tensor hyper. Now, this kind of boundary condition, so this obviously is a different boundary condition from what we have seen before, and this basically consists of an O5 plane with a stuck NS5 brane. Okay, so all these type 2b boundary conditions have been discussed in some detail in this paper by Hanani and Zaffaroni, and it's nice to see how it fits into these quivers that we have. Okay, so these two infinite families of quivers will be the basic topic of our talk for the rest of the talk. But just for the sake of completeness, let me say what happens when you consider singularities of only the D type. So again, if gamma 1 is Dn and gamma 2 is trivial, then this is again a very well-known example of a mirror dual, also covered in Jan de Boer and collaborators' papers. when both of them are D with even integers, n and m, then you have a mirror dual of this kind. They are both affine D-type quivers with alternating SO and SP groups in the bulk, and then SPK groups here at the boundary. It gets even more interesting when you make one of them odd. Then you have an affine quiver here and a truncated quiver here, and the truncated quiver ends in a U2K gauge group as opposed to an SP or an SO. Okay, and similarly, you can make both of them odd, and then this is like a self-dual quiver. Okay, so now let's try to see what S3 partition function can actually teach us about these infinite families of quivers. So let's recall the basic idea. So the basic idea was in the IR limit, the S3 partition function of n greater than or equals to 2 SUSY theories localized to a matrix model integral, which looks of this form, sigma being the vev of the adjoint n equals to 2 scalar. Now what we try to do is to show that such partition functions as functions of masses and Fi parameters agree on both sides of the duality. That's the check of the duality, right? Now, apart from being a naive check, this procedure actually teaches you more in the sense that it tells you what exactly are the correct parameters to count in a given duality. So given two dual theories, you might often see that the masses on one side do not match the number of Fi parameters on the other side. Okay, but this S3 partition function tells you which are the ones which are the masses or Fi parameters can be eliminated by simple change of variables. Okay, so you obtain a certain a certain fundamental set of masses or Fi parameters that you should now compare to the other side of the duality. Now, the matrix model for arbitrary finite rank of this gauge group is a very hard thing to do. Now, large n results exist for a large subset of these theories, and this is the subject of the papers by Herzog and collaborators from 2010 to 2012. But that's not what we want. We don't want large n results. We want to solve the problem for finite rank of the gauge group. Okay. So what should be the strategy? The strategy should be to try to manipulate the partition functions of model A using some clever change of variables and show that it is identical to the partition function of model B, and in the process making the action of S duality at the partition function level explicit. And then basically compare the two partition functions as functions of mass and Fi parameters, and that directly gives you the mirror map. Now, it turns out that this manipulation is also difficult in general, and one needs very non-trivial identities using hyperbolic functions to do that. Now, I'll show at least one of those identities. So let's recall what Kapustin and collaborators did with the affine A-type or the circular quivers. So basically, what you can do is that you can write the partition function, the matrix integral for the partition function of these quivers as a product of these NS5 and D5 contributions. Okay. Now, then a certain change of variables basically swaps D5 and NS5, and using certain identities of hyperbolic functions, you can show that the two theories are equivalent. Now, there were two identities which played a crucial role in doing that. One is the fact that a hyperbolic sec is the Fourier transform of a hyperbolic sec is a hyperbolic sec, and the second one was this Cauchy determinant identity. Now, this is a very, very nice thing to look at, because on the right-hand side, you see that it's the contribution. I mean, well, I did not really mention what are the NS5 and D5 contributions, but if you're familiar with with Kapustin's paper, then you'll immediately realize that this is the contribution of an NS5 brane, while 1 over this cosine thing is the contribution of a D5 brane. So this is, in some sense, rewriting the contribution of a D5 in terms of rewriting contribution of an NS5 in terms of the D5s. Okay. So that's how the duality basically works. So we try to do the same thing, carry on the same program here. So in our case, in addition to the NS5 and D5 branes, there are boundary contributions, which we call F1 and F2, coming from these half BPS boundary conditions that could be, for example, orientifold, orbifold, 5 planes. Right? And there are, again, 2 identities which play a very crucial role here. The Fourier transform of cosec hyperbolic and what is known as Schurz-Pfaffian identity. Just to show you how these 2 can be used as building blocks for more complicated identities. So this, for example, is one. And here, this is the more gory-looking one, the other. Now, identity 1, it turns out, is all you need to implement S-duality for orientifolds where there are no stuck branes. Okay? So to remind you, these were theories which had SP gauge groups at both ends. Okay? So such theories are the ones which corresponded to orientifolds without any stuck branes. And for that, this identity plays a crucial role. I mean, this is the identity that implements S-duality. For theories with stuck NS5 branes, the implementation of S-duality is trickier, and this is the identity that you need to use to implement S-duality in such cases. But it does not have any interpretation as NS5, D5 contributions that you have in the other cases. So it's kind of a little more murky as to what this really means in terms of the in terms of the boundary conditions that you have from string theory. So as an example, just to show how things work, this is an example of quiver which do not have any stuck NS5 branes, so end with SPK on both sides. And if I write down the partition function of the A-type theory, I know this looks terrible, but I'm just going to say which terms mean what. So this is the contribution of the single So here S is equals to 1, so which means that you have 1 hyper here and 1 hyper here. So this is the contribution of the 1 D5 brane that does that, and this is the contribution of the n minus 2 NS5 branes in the quiver, and these are boundary terms, these tan hyperbolic stuff. So this tan hyperbolic, remember, was the Fourier transform of 1 over sine hyperbolic. Okay, so these are the contributions of the boundary terms, the tan hyperbolic ones, while the other ones can be clearly identified as NS5 and D5 contributions. Okay, so so before going to the counting, let me show you the other case. So this would be the case where you have a stuck NS5 brane. Okay, you have an SPK on one side and U2K on the other side. Okay, and for that, you can clearly see that on the one side you have this tan hyperbolic contribution, and on the other boundary you have this more complicated cosine term, while the other ones could be easily identified as NS5 or D5 contributions. Okay, so just like with NS5 and D5 contributions, you can build any quivers that you want at the level of the partition function. With these, knowing these guys, you can basically use orbifold 5 planes or orientifold 5 planes as building blocks to build quivers such as these. Okay, so it just increases the number of building blocks that you have. Now, let me talk a little bit about how one derives the mirror map and fixes the counting of parameters. So if we look at this quiver, for example, you see that there are, a priori speaking, 2s fundamental masses on one side, and s minus 1 Fi parameters on the other side. Okay, so that seems to be a problem because the number of masses on one side does not match the number of Fi parameters on the other side. Okay. Now, the S3 partition function gives you a recipe to cure that problem, in the sense that it tells you that if this theory has to be dual to this other one, the masses of these hypers better be pairwise equal to each other. Okay, so if that is the case, then one can show, again from writing down the partition function, that the effective number of masses that you have is s minus 1. Okay, after you implement this thing. It also tells you that for this duality to work, the Fi parameters of this boundary node must be equal to the Fi parameter of this boundary node. Okay, or in other words, there seem to be a Z2 discrete gauge symmetry that you need to mod this quiver by in order to get the correct dual theory. Okay, after you have done that, then of course the number of masses and the Fi parameters agree on both sides. Okay, and then you can simply read off the mirror map by comparing the two S3 partition functions after you have done whatever I said about the manipulation of S duality, etc. And it looks very simple and is consistent with what you would expect from type 2b description of these quivers. So let me move on to the conclusion. So what I tried to what I showed initially was that mirror symmetry in n equals to 4 affine quiver gauge theories have a nice description in M theory, and it's a very useful tool in classification of mirror duals. And it also serves as a convincing check for mirror symmetry, and especially to extract the mirror map, which could be pretty complicated for non-trivial quivers. And we extended the study of S3 partition functions for mirror duals in this particular class of dual theories, which involve orbifold, orientifold 5 planes in the type 2b picture. And we also showed that there are two distinct kinds of boundary conditions that you need to consider in this picture. Theories can have any one of these boundary conditions or both. It's like a building block that you can use to come up with any quiver that you like. And the computations indicate that there are deeper structures that we do not understand yet. For example, this Z2 discrete gauge symmetry that you need to have in order to make this duality work is something that one would like to understand better from the field theory perspective. Okay, there are several future directions of this project. One is, of course, understanding the D cross D theories, I mean, some of which I showed you. One would like to compute some more exact quantities, like the compare the squashed 3-sphere partition function, and particularly this S2 times S1 index for this class of dualities. One might also like to understand the moduli spaces of these dual theories in a more direct fashion, in the way that Gayotov and Korotev addressed the problem for the linear quivers recently, and also their relationship with integrable models. A completely different direction that I did not talk about at all is the computation of counting of chiral operators, which are also gauge invariant on the Higgs branch of these theories. And this is a work in progress with several collaborators. And finally, one would like to understand the large n limit of these partition functions and study the gravity duals. Now, part of this work has been done for circular quivers by Essel, Bacchus, Estes, and Gomis. But understanding them for the D-type quivers would indeed be a really nice thing to achieve. So on that note, I would like to thank you for your attention. Thanks. Go ahead.
So you had some pretty gruesome identities back there.
Yeah.
Do you have proofs of those identities?
Yeah, in the paper, yes. Yeah. Which one? The cosine one? Yeah. All of them were gruesome.
The one with the Fafian in it. Then.
Oh yeah, this one.
Yeah.
Yeah. Yes. So yeah, this has the proof is there in the paper. Yes. Yeah.
How do you prove them?
How do you prove that? So combinatorics.
Okay.
Yeah. I mean, combinatorics is a fashionable word. I mean, just looking at it and trying to manipulate it.
How's the original research on?
Original one? This one?
That was just
This one?
by explaining out. Just, yeah.
Yeah. No. This is easier actually. So this is like so if you consider a matrix which of the form say Aij is of the form 1 over xi minus I guess xj, then you can write out the determinant in a product form. And this is slightly more general than that. I mean, you can also do that for something like say xi minus xj divided by some function gxi. Yeah, but it's understood. Yeah, it looks very kind of mysterious, but it's.
Do you know if you can play this kind of tricks for 5D series? 5D fluid series?
What do you mean? I mean, one has to look at exactly the contributions.
It seems to be useful for doing matrix model calculation.
Yes, it's very useful for matrix model calculation.
5 dimensions, you will have things which are not, will not be of, I mean, the powers of things. I mean, when you change the dimensional theory, the determinants that you're getting.
No, that doesn't depend on that because it depends on exactly like the Cartan of the gauge group, basically. I mean, you're taking.
Yes, but the factors which come out will be very different.
The functions might be different, but as long as they have,
Well, sometimes you plainly just doesn't have a structure where you have your return of similar structure.
Well, yeah, I mean, if you have the gamma functions instead, then you still have some kind of structure like
I just
that.
wonder if there are more general identities than this one.
No, there might be. I think. The hyperbolic functions arise as limits of course, much more complicated functions, and those do have much more complicated identities. So one would think that, but these are the simpler forms. Yes. I mean, for example, if you're looking at partition functions on S4, I mean, they're the functions that arise in the one loop contribution. They probably are much more complicated. I mean, you cannot probably come up with identities like this. I don't know. Yeah. Well, yeah, maybe we can talk about that. Sure. But yeah, to answer your question, I mean, these all have proofs. Yeah, they're all done in the paper.